Hello and welcome to Infinite Insights.
In PNC, many people just memorize formulas like these and hope they don't mix them up. Today, we're moving beyond memorization. We're going to use the box method to make the factorial feel intuitive, and then use that logic to derive the formulas for permutations and combinations from scratch. By the end, you'll know exactly why these formulas work. Let's start with the rule of product. Before we can talk about where the factorials come from, we need to talk about the fundamental principle of counting, the rule of product. If one event can occur in m ways, and for each of these ways, a second event can occur in n ways, then the total number of outcomes is m times n. To illustrate this principle, suppose we roll two six-sided dice. What is the total number of ways the dice can land? Let's name the two dice A and B. Die A has 6 possible outcomes. For every single one of these outcomes, die B also has 6 possible outcomes. If you laid these out in a table, you'd have 6 rows and 6 columns, giving you exactly 6 times 6 equals 36 unique outcomes. If we introduce a third die, we move from a flat 2-dimensional table to a 3-dimensional cube of outcomes. Although a 6x6x6 block is harder to visualize, the principle remains the same. We multiply the possibilities for each independent stage, giving us 6 times 6 times 6 equals 216 unique outcomes. In our dice example, the number of choices stayed the same for every step, but this is not always the case. Consider this example. Suppose we have a suit of 13 distinct cards. How many different ways are there to arrange the cards in a row? A good way to visualize this problem is using the box method. Imagine we have 13 boxes or slots in a row, which need to be filled with exactly one card each. At the start, there are 13 cards to choose from, so there are 13 ways to choose the first card. But then, we only have 12 cards left, so there are only 12 ways to choose the second card. This process continues until we reach the last card and slot. So there is only one way to choose the last card. Using the rule of product, the total number of ways to arrange the cards in a row will be 13 times 12 times 11 and so on until 1, which is the same as 13 factorial. We can generalize this to any number of items n. There are n ways to choose the first item, n minus 1 ways to choose the second, and so on until the last item when there is only one way. Therefore, there are n factorial ways to arrange n items in a row. To derive the formula for permutations, we need to make the problem more general. Instead of choosing all 13 cards from the suit, suppose we only want to choose 5. How many different ways are there to arrange any 5 of the cards in a row? We can use the same approach as before, this time with just 5 boxes. There are 13 ways to choose the first card, 12 ways to choose the second, 11 ways to choose the third, 10 ways to choose the fourth, and finally 9 ways to choose the last card. Therefore, the total number of ways is 13 times 12 times 11 times 10 times 9. This looks like the first couple of factors of 13 factorial, but each factor from 8 onwards is missing. It's the same as if we took the factorial of 13 and then divided by the factorial of 8. We can rewrite it like this: 13 factorial divided by 8 factorial. Also, notice that we can get 8 by taking 13 minus 5, where 5 was the number of items to be selected. Now we can generalize this rule. To permute r items from n possible items, you have n ways to choose the first item, n minus 1 ways to choose the second item, and so on until n minus r plus 1. Therefore, following the same logic as before, the total number of ways is n factorial divided by n minus r factorial. This is usually called npr or n permute r. Combinations can now follow as an extension to permutations. A combination is a selection where the order does not matter. This means that we only want to count unique selections, and rearranging the same items in a different order does not increase the number of combinations. In this example, r is 5 since we're choosing 5 elements. We already know that the total number of permutations is n factorial divided by n minus r factorial. For every possible selection of r items, there were r factorial ways of arranging them. So in the number of permutations, we have double counted by r factorial times. To remove this double counting, we need to divide by r factorial, which will then give us the number of possible combinations. This brings us to an interesting relationship. The number of permutations is r factorial times the number of combinations. And there we have it. We've derived the most common formulas for permutations and combinations from simple principles. I'd love to hear what other STEM topics or other video ideas you want me to explore next. Let me know down below in the comments. I'll see you in the next lesson.